Hello, everyone. Today is the last lecture about visualization. We will finish the last 10 slides about ggplot2, and then your quiz will start at 2:30. It's available on Canvas. You don't need to stay in Zoom, okay, on Zoom. You can just, leave the meeting. Um, all right, let's start. So last time we talked about graphical displays for one numeric variable and graphs for one categorical variable. So today we'll start from this case, two categorical variables. We want to study the relationship between two categorical variables. Okay, and so let's still use the data set about homeless people who use substances. Let's consider a different categorical variable, a substance. And this variable has three categories: alcohol, cocaine, and heroin. Three drugs. Alcohol is not a drug. Substance. And we already have one categorical variable, which is homeless status, two levels, homeless and housed, okay, two levels. Let's try to display the relationship, show the relationship between homeless and substance. Okay. Ideally, we can create a three-dimensional bar graph to show the relationship. So the first two dimensions are corresponding to the two variables, and the height of the bar will show the count in each combination of levels of the two variables. However, usually three-dimensional plots are criticized by researchers, statisticians, um, mainly because human eyes are not really good at reading or understanding three-dimensional plots. Okay. So instead, we can create a flattened version of the three-dimensional bar graph. Namely, we can use color saturation to demonstrate the third dimension, which is the count. Okay. So last time we actually talked about 2D two-dimensional bin plot. Okay, so this one is similar, but this is for categorical data. Okay, and there are some other differences. Okay, let's take a look. First, we use the width function to create a joint table for homeless and substance contingency table for these two variables. So homeless status and substance, and the cells contain the counts for each combination of levels. For example, 103 people in the sample data set are homeless and they use alcohol. So this is the joint table. Now let's see how to create a tile plot. So take the data set. So in this chunk of code, we actually use some operators like this, percent greater than percent. So this is called a pipe operator or pipeline operator. We will talk about it in more details in the next module, data wrangling. But for now, let's just try to use it first. Okay, it's kind of like an operator that can connect different commands together. Okay, and the order is from top to bottom and from left to right. Okay. So let's take a look at this. Take the data set and group the data by substance and homeless at the same time. Okay. Then we summarize the data. Okay. We create a new variable called count, which is equal to the number of observations in each combination, in each small group, created by substance and homeless. Okay, for example, so this step will calculate these six numbers in a table somehow. Okay, we call it count. And then this variable will be available for us to use in the next step. Right? In the next step, we will create a plot using ggplot. In the mapping part, okay, X is substance, Y is homeless, and fill is equal to count. This count is created in the last step. Okay? And then lastly, we add a layer of tile plot using gem tile. So this is the plot. So it's very similar to the two-dimensional bin plot. You see, by default, it will use this kind of blue color shade, right? And the lighter the color, the larger the count, actually. And so there is at least one difference. You see the third dimension, fill equals count. This variable has to be calculated, or it should be available before we call the function, when we use the function, right? But when we do the two-dimensional bin plot, the third dimension is corresponding to the sort of it's also count, but we don't need to calculate it by ourselves, right? It's automatically calculated in the background of the function. Okay? So two-dimensional bin plot will automatically calculate the count for us, but tile plot will not. Okay? You have to provide this quantity. All right. Alternatively, we can create stacked bar plots to show the relationship between two categorical variables. So usually the main question is, are these two variables related or not, or associated or not, or they are independent? Right? So this type of plot can help us to answer that question. So let's see how to create a stacked plot. So first, ggplot specify the data set. X is homeless, and we map substance to fill, which is the color of the bar. So this will separate each bar to three segments. Each one is corresponding to one substance, and then add gem bar. So we have this plot. This is called a stacked bar graph. The y-axis is corresponding to count by default. However, although we can see some differences between the two bars, so namely we want to know if the distribution of substance is the same between the two groups of homeless status. So we want to know if the distribution of substance is the same. So although we use count, we can still see there is some difference, right? For example, the cocaine. So this segment is smaller among homeless people compared to the segment in housed people. A better way to create this stacked plot is to use proportion for the y-axis for the height of bar. We just need to add this argument, position equals fill in gem bar. Then you see that the height of the bars will become 1 for both bars, and also so the height will be corresponding to proportion. And we can easily see that this plot can help us to sort of compare the conditional probability of substance given homeless, right? Because each bar has the height 1, which is 100%. For example, you see for homeless, this group, 50%, about 50% of people use alcohol. It's very clear from 50 to 100, so 50%. But among housed people, only about 30% use alcohol. And you can see the difference very easily. The difference is very obvious because we make them have the same height. So this is a good way to answer questions such that, for example, is there a higher chance of using heroin if the person is housed as opposed to being homeless. If you compare these two, parent, yes, right? If it's housed, the proportion is higher, is bigger than homeless, right? So we are essentially comparing this probability of parent given house and probability parent given homeless. So are they equal or not? So definitely not equal. Housed is higher than homeless. So whenever you want to answer questions about conditional probabilities, you should consider this argument: position equals fill. And also pay attention to the definition of the event and condition in the question. So in this case, you see homeless status is the condition, and the event of interest is about substance. And another option is to use a dodge position. So first define the ggplot part as G, and then we first let position equals dodge. Then you see this is the bar plot. So we have two sets of bar plots. So for each homeless status, we have a set of bar graph for substance. You can compare the patterns. Apparently they are very different, right? And this is the one that we got in the last slide. So you can compare these. They are kind of equivalent. They display the same information. From these two plots, we know that homeless status and the substance they use are not independent. Okay? They are related or associated, apparently. If they are independent, we should observe very similar patterns for these two bar graphs, or similar decompositions of the three substances in each bar. All right, so this is another example when the condition is substance. If you want to answer questions such as what is the proportion of homeless whose primary substance of abuse is heroin? So in this case, the condition is the substance, and the event of interest is homeless status. In this case, we should switch these two arguments. So now X is substance, Phil is homeless. Right? In the previous example, we have X equals homeless and Phil equals substance. And you can answer some questions in this scenario when we consider substance as a condition. All right, then let's quickly move on to the next topic. We can also use bar graphs to show ordinal data or discrete numeric variables. Discrete numerical variables are numeric variables, but there are only a few distinct values. For example, in the MPG dataset, the cylinder variable is a discrete numeric variable. It only has 4 levels, 4 distinct values, 4, 5, 6, and 8. And there is no 7 in between. Okay, so this is not a continuous numerical variable. In this case, so this is a frequency table for cylinder, only 4 levels. If we just directly create a bar graph using this variable cylinder, we will have a bar graph like this. So you see, there is so the level 7 is reserved, although there's no data points in this in this group or for this value, but still the bar graph will leave an empty space for it. That is because it considers cylinder as a numerical variable. It thinks they're kind of like so not something is missing. It's just that no observations are observed in this interval, but it is still a valid value. Okay? However, we know that this is not a valid value at all. Okay? Cylinder can never be equal to 7 in the data set. So a better practice is to first convert cylinder into a factor. And then, so see, x is equal to s the factor cylinder. And then it will not, it will only consider the available values in the cylinder column. It will not consider 7 or other values. And then we have a bar graph like this. Okay, so this is more appropriate for discrete numeric variables. Just pay attention to that. Um, yeah. And then let's move on to the next group of data. We have one numeric variable and one categorical variable, or two categorical variables. We want to study the relationship between one or two categorical variables and one numeric variable, grouped data. For example, we can create a side-by-side plot for a PCS in the homeless data set. PCS is physical component score, which are some numeric health measurements for those individuals in the data set. So the lower the score, the worse the status, the health status of the person, or those people. This is numeric. We want to compare the distribution of PCS among different substances and also homeless status. We have two categorical variables here. We can show them at the same time. So let X be homeless and Y be PCS. Okay, so we have a vertical side-by-side box plot and add a layer of box plot. And finally, we can use the facet wrap to add substance. Okay? So create a panel for each substance. Then we have this side-by-side box plot. Okay? So it looks very neat, right? And you can have some observations or have some conclusions from this graphical display. For example, within each substance, you can compare the PCS distribution for homeless and housed people. So for example, housed people have higher median than homeless people, which is intuitive in general. And also in the cocaine group, the medians are similar, but still housed is slightly higher. And for heroin, median is higher still. And you can also compare their spread by comparing the range and interquartile range. Range is max minus mean. Interquartile range is Q3 minus Q1. Okay. All right. So this is a side-by-side box plot. A variation of that plot is a violin plot using the gene violin function. So this is a very basic look of a violin plot. You have the option to change the colors of these violins. One advantage of a violin plot is you can actually see the kind of the density of observations in each group. The wider the wider the area, the more observations in that area. Okay, we can see different shapes, but we cannot tell where the median is. It will not show the median by default. And another way to compare different numerical distributions or grouped data is to use frequency polygons. Frequency polygons are similar to histograms. So what is a frequency polygon? Let me show you a simple example. Suppose we have a histogram somehow like this. Then a frequency polygon will will connect the peak of each bar in the histogram and connect them together. So for frequency polygon, bandwidth or bandwidth is also a parameter. It determines how big the each interval is. Okay. And one advantage of frequency polygon is they only describe the outline of the histogram, right? No bars. So that if you have multiple groups of data and they overlap a lot, if you create a histogram in the same plot panel, they will overlap with each other. You cannot some of the histograms will be hidden in the background. But if you use frequency polygon, you can see all of the distributions. So in this plot, we use a diamond data set. Let X be price. So this is a primary variable, the price of the diamonds. And we map cut to color. So which means we'll create a frequency polygon for each cut, 5 levels. And then add a layer of GM frequency freak polygon. So this looks like this. And by default, the y-axis is corresponding to count. This is not the same with GM polygon. Last time when we talked about the maps, creating a map, we use GM polygon. The polygons are kind of used to create something like this. And frequency polygons are different. Okay, so they are similar to histograms. Okay? And you can definitely change the y-axis. For example, you can choose to use density instead of count. By default, it's count. Then you make all of the frequency polygons have the same scale for y. They are on the same scale so that you can compare the distributions better. And the last plot is for 2 or more numeric variables. Okay. For 2 numeric variables, usually we create a scatter plot to show the relationship and show the pattern, right? And so now we will take a look at a more advanced version of scatter plot somehow. It's called contour plot. So this is actually a 3-dimensional plot on a 2-dimensional plane. The third dimension is the joint distribution of x and y, or density of x and y. F, x, y. If the 2 variables are x and y. Right? So we know that if we, for example, x follows a normal distribution somehow like this, and y also follows a normal distribution. Just one example. So y will follow is a normal distribution too. If we plot them together, if we use a 3-dimensional plot, it will be like this. Okay, so it's like a mountain. It's like a mountain, and the third dimension is the joint distribution. Just the height of the mountain is the joint distribution, joint density of the 2 variables. And if we calculate them and connect sort of all of the f(x) and y, same value f(x) and y together, okay? Then we will have something like this, okay? So these contours are used to show the height of the mountain, okay? So now imagine you project the third dimension, okay? down to the two-dimensional plane, and then the contours will look like this in this plot. So the points on the same contour have the same joint density value, f, x, and y. Okay? So we can use this function to create it. Right? So in this plot, we first create a scatter plot. So see, SAT 2010 is the data set. Right? The the two variables are math and salary of the teacher, salary of the teacher, and then add a layer of points. I save the result in G. So G is the scatter plot. And then we add a layer of contour plot. Right? So using this GM density 2D, and there is a mapping. We map the level after that level to color. And by default, it uses the color saturation of the blue color. Again, the lighter the color, the higher the level, right? The larger the value. Right? So it's indeed somehow like a mountain. Right? So this is the topest. And alternatively, you can create a filled two-dimensional uh, filled contour plot. Right? Just take G and add GM density 2D field. Right? Alpha is used to control the transparency of the colors. Right? So by default, it used this kind of color palette is the Verdis color palette. And pay attention, the legends were in the opposite in a descending order. Okay, so this is the lowest level purple, and yellow is the highest level. If you carefully observe the value range, right, for each color. So different from here. Here from lowest to highest, but here from highest to lowest. Just pay attention. So it looks better. Actually, this one looks better. And all right, I think right on time. So now it's 2:27. Okay. Uh, if you have any questions, you can stay. Otherwise, feel free to leave. And I will see you guys next Tuesday. Okay? Have a